Hello, good afternoon, and very warm welcome to all of you, especially all the people, especially everyone who's come from many colleges and high schools and so on from the different parts of the city for this very special lecture. And of course, to all the program participants who are here for our workshop on quantum information. So it's a pleasure to welcome you to this special ICTS distinguished lecture, for which we are very happy to have Professor Rob Myers from the Perimeter Institute telling us about why, as humans, we explore, I think. And I think it's a topic very close to the heart of all of us who are in science, and probably for many of you who want to embark on science. The ICTS Distinguished Lecture is a very special event that we have, in which we have eminent scientists come and tell us, share with us their vision. So it's, as I said, a great pleasure to have Professor Rob Myers here today. Rob is a string theorist, but a very broad theoretical physicist as well. And I'll say a little bit about his interests, but he's also currently the director and the BMO Financial Group Isaac Newton Chair at the Perimeter Institute for Theoretical Physics in Waterloo, which is in Ontario, Canada. The Perimeter Institute, for those of you who are not so familiar, is one of these very novel experiments in creating a high-quality center for theoretical physics, and very broadly interpreted, and which has really sort of rocketed to high visibility, especially in many of the frontier areas of physics, and has also been very actively engaged, like ICTS, in research, in not only research but also outreach and so on. It's a particular pleasure to have sort of a sister institute, the person from a sister institute here with us. So Rob joined Perimeter, in fact, as one of the founding faculty in 2001, and was the interim scientific director from 2007 to 2008, and became the director in 2009. And before that, Rob was at McGill University. So his range of interests in physics are very broad, as I said. Some of his very early contributions are in purely gravitational physics in Einstein's general theory of relativity. You might have all heard of the Schwarzschild solution of black holes. There is a rotating version of it, the Kerr solution, and these are solutions of Einstein's equations of general relativity in 4 dimensions. Rob, together with Malcolm Perry, found very novel generalizations of these 2 higher dimensions, which have played an important role in the theoretical understanding of general relativity. They are now called the Myers-Perry black holes. He has worked on a number of aspects in string theory since his PhD days in Princeton. One of the very novel effects in string theory, which arise due to the presence of objects called D-branes and them kind of blowing up in the presence of electric-like fields, is called the Myers effect. So Rob is a person who has made fundamental contributions. Among his current interests are the theme of this program, that of quantum information and gravity, and how it ties up with how they come together in trying to understand fundamental questions such as the black hole information paradox. So amongst the many honors, Myers has been awarded the Herzberg Medal of the Canadian Association of Physicists, the CAP-CRM Prize in Theoretical and Mathematical Physics, and several other medals, and which I won't list because it's a long list, and you will find them on his Wikipedia page. So I just want to end by saying that Rob is a very passionate sort of a champion for science, and today I think it's particularly apt that he will talk about this theme of why we explore. We'll have his talk, and then after that there will be time for plenty of questions and answers. So please hold your questions till the end, and let me invite Rob now for his lecture. But please do it.
Thanks. Okay, thank you, Rajesh, and good afternoon, everyone, and thank you for joining us here. As you've just heard, I'm a theoretical physicist, and over my career, my research has touched a wide number of topics, from string theory to quantum matter, from black holes to cosmology. Most recently, as Rajesh was saying, my research is focused on the connections between quantum information science and quantum gravity. And in fact, that's what brought me here to the ICTS to join or to participate in this ongoing program this week. And I imagine that when Rajesh first asked me to give this talk, that he expected that I'd be giving a talk about the intersection of quantum information and quantum gravity. And a talk like that would have probably started with this slide here. And with the picture here and a bit of a story, what I would have been trying to convey to everyone is the excitement that my colleagues and I feel about the research that we've been doing and our collective progress in recent years. But of course, that is not what I'm here to talk about today. Instead, I chose another topic, but one that's still near and dear to me, and I think one that should be near and dear to everybody in this room here this afternoon. And as was being described, that's because I have another job back in Waterloo. That's a relatively small city in the heart of Canada, but it's one that has a big reputation in science and technology. I have this other job, and that job is as director of the Perimeter Institute. And we study a wide range of topics, cutting a broad swath across modern theoretical physics, from cosmology to quantum information to particle physics, or as we sometimes like to say, from the infinite to the infinitesimal. At Perimeter, we have faculty, we have postdocs, we have students, and all of them, like me, are pursuing deep questions, probing the boundaries of our understanding in theoretical physics, searching for answers in a universe of questions. I think my job as director is one of the best jobs in the world. You see, I get to lead a team of 200 young innovators and explorers. They're really trailblazers exploring new frontiers. And this is a journey of discovery. It's a journey of the mind where we take on some of the deepest and most profound questions about the inner workings of the universe. Of course, Perimeter is only one of a constellation of universities, organizations, and institutes around the world that are filled with explorers, all on journeys like the one that I was just describing. And of course, the place where we're all gathered here this afternoon, the International Center for Theoretical Sciences, is another one of those magical places. Here in India, the contributions to physics run deep throughout the history of science, from the very ancient times to the modern day, from the introduction of the concept of zero to an understanding of the formation, the structure, and evolution of stars. And so the ICTS is really building on a long tradition here in India. Researchers here are experts in areas from physical biology and complex systems to gravitational wave astronomy and string theory. Wider, perhaps, than the topics covered at Perimeter, but sharing a very common spirit. Our explorations push the boundaries of human knowledge. It's incredible and it's exciting work, but let's be honest, sometimes it's a little hard to explain. But as an institute director, much as Rajesh, I'm sure feels the same, it's a part of my job to translate what we do to a language that can be understood by politicians, government officials, by businessmen, private donors, and just science enthusiasts. Of course, I usually begin by trying to convey the sense of excitement that we all share about our research, but eventually, and often very quickly, the conversation turns from what we do to why we do it. And as physicists, that why is understood intuitively. We do it because we're excited and we're driven by the explorations themselves. For us, perhaps, it's obvious that the desire for new knowledge, the quest to expand the frontiers of our understanding is and always has been a part of humanity. As people, we all share the same excitement. We're bound together by a shared curiosity. And that curiosity, I believe, is an essential element of the human condition. However, when most people I talk to are asking why we study theoretical physics, that's not the answer that they're looking for. That's not an answer that a politician or a donor is going to be satisfied with. What they're really asking is, what is your research good for? And so tonight, I want to try and address that question a little more seriously. What is fundamental research good for? Or put another way, if we are explorers, why do we explore? Now, theoretical physicists are fans of thought experiments, and so, if you permit me, I'd like to start there today with a thought experiment. So imagine a city, perhaps London or Paris or New York, but at the end of the 19th century, about 130 years ago. It's a very different world, but you might recognize the spirit of the time. In the last few generations, there have been enormous advances. We've seen the innovations like the telegraph, steam power, transcontinental railways. Living standards have increased dramatically. Cities have grown by leaps and bounds, becoming great engines of economic growth and prosperity. However, with those great changes have also come large challenges. Overcrowding, disease, urban poverty, civil unrest. And so, in 1898, delegates from cities around the world gathered in New York City for what was the world's very first urban planning conference. Now, at that conference, there was one overwhelming problem that dominated the discussion. It wasn't infrastructure, it wasn't housing or poverty or economic development. It was, It was horse manure. You see, everything and everyone in those large cities of the Western world were moved by horses. So, for example, in New York City, where the conference was held, there were over 100,000 horses, and together they were producing 1 million kilos of manure every day. It was ankle deep in some streets and knee deep in others. In London, the famous paper, The Times, they predicted that by 1950, every street would be buried 9 feet in horse manure. This was happening in cities all around the world, and it was an environmental crisis and a public health crisis. So now my thought experiment begins by, let us imagine that in one of those far off in time cities, there was a committee formed with the task of investing funds to build a better future. A young man comes in the room and sits down. He says, "I'd like a small grant." So the committee asks, "For what?" "Well, for my work. I need a desk, a blackboard, maybe a shelf for my books, a small stipend so that I can go to a few conferences." And they ask, "Well, what are you working on?" And he says, "Well, I have these ideas about light. It's very complicated," but at that point, the committee cuts him off and they say, and I flip the page around, sorry. And they say, "Excuse me, Dr. Einstein, but what's that got to do with horse manure?" So Einstein never actually applied for municipal funding, but let's imagine the return on investment if he had. Einstein is often portrayed as the ultimate abstract thinker, someone whose ideas have never had or have an effect on our day-to-day life. But in fact, his ideas set a foundation for a myriad of devices and technologies that we take for granted today. Without Einstein's foundations, we would not have semiconductors, not computers, no lasers, no GPS, no modern medical imaging. It's a very long list. But let's pick one of those examples, a smartphone. Now, I'd be willing to wager that most everybody in this room carries one of these in their pocket. Now, much more than a phone, these marvelous gizmos are connectors, enablers, and amplifiers. Here, a farmer in Nigeria, using her cell phone, she can connect to financial services, she can get weather information, she can coordinate the transportation of her crop. Anecdotally, I can say that half of the apps on my homepage here are actually different ways in which I can connect with my daughters as I try and get their attention amongst their busy lives. In fact, I found that using this as a telephone is perhaps the least effective way to connect with them. In any event, when our farmer in Nigeria or one of my daughters uses her phone, she is benefiting from 2 centuries of investment in theoretical physics. This device relies on Maxwell's electromagnetism from 150 years ago. It relies on Einstein's relativity from 110 years ago, and it relies on 100 years of quantum mechanics developments. It's in fact a triumph of theoretical physics. So when I conduct this thought experiment, perhaps with a government official or a private donor, I hope that I'm convincing them that investing in theoretical physics is a good idea, that it will, with time, generate a whole new generation of gizmos, the ones that will shape the lives of our great-great-grandchildren. Now, that is true as far as it goes, but this afternoon I'd like to go further. Remember where we started with this thought experiment. It was a world in trouble. Our world today, like the one that I described, does face many urgent problems, and the problems are real, and we must confront them with speed and energy and creativity. And yet the lesson of the thought experiment is that we must not set our horizon with our problems, because the horizon of our imagination is just so much larger than the horizon of our problems. Now, as a physicist interested in gravity, I think a lot about horizons, literal horizons and figurative horizons, horizons we can prove exist mathematically and horizons that we can see. Black holes are perhaps one of the most interesting objects in gravitational physics. They're bottomless pits in space and time. They are characterized, in fact, by something that we call the event horizon. And this is a surface where the gravitational pull has become so strong that nothing, not even light, can escape from inside. Hence, it's literally a boundary beyond which we cannot see. And it looks something like this. This is a photograph of the event horizon of a black hole in a galaxy known as M87, and it was taken by an experiment known as the Event Horizon Telescope. Now, M87 is really a monster. It's 6.5 billion times the mass of our sun, and it spans a space that's 4 times bigger than our entire solar system. It's really, really huge. But it's also 55 million light years away, at the heart of a completely different galaxy. Now, I'm told that here in Bangalore, that you like to measure commuting distances by the time of travel. And so, in this case, what I just told you is that the light that made that image on the screen had actually been traveling for 55 million years. Now, to get something that far away into focus, we'd need a telescope here in Bangalore that would allow us to read a newspaper in Baghdad. Or alternatively, I like to say that it would allow us to see a hockey puck on the surface of the moon. And that's because I'm a Canadian and I'm a big fan of hockey, but perhaps that's not the right analogy for this evening or this place. And so let's say that I need a telescope to see a cricket ball on the surface of the moon. Now, when it comes to black holes, we've been speculating and theorizing and even making indirect observations for decades. But 5 years ago, when this picture was first unveiled, it gave us something completely new, direct visual evidence that black holes exist. Again, this is not a simulation, it's not an artist's impression, this is a photograph, and it's one that captured the imagination of the world. In fact, it appeared on the front page of nearly every newspaper around the globe. It's been estimated that 4.5 billion people have seen that image. Now that's half the population of the world. This image then is something that's transcended science and entered popular culture. In fact, a copy of this image is hung in the Museum of Modern Art in New York. Now, not only can we see black holes, but perhaps you remember this. So this is the exciting part of the talk. Oh, it works. Thank you to the IT team. What you're hearing here is a signal captured by LIGO, that's the Laser Interferometric Gravitational Observatory. And that signal was captured in 2015. And it's actually a gravitational shock wave that was created by the collision, sorry, the lights. By the collision of two black holes, both about 30 times the mass of our sun. And for a few milliseconds, the energy that went into into the gravitational waves was more energy than emitted in all the light of all the stars in the sky. Now, it was 10 years ago when we heard that first chirp, or the scientists at LIGO did. And now the detection of gravitational waves from similar mergers has become a regular event. And a whole new way of looking at the universe has opened. So what are gravitational waves? Well, there's a lot of equations and a lot of complication. But basically what Einstein told us is that when giant masses move around, that they generate waves that stretch and squash the very fabric of space and time. And when those two black holes crashed into each other, they generated a tsunami of a gravitational wave. And yet, these waves had to travel across the cosmos. And so, in doing so, they had lots of time and space in which to spread out and die down. And so, when the first wave was detected here by LIGO, it had traveled more than 1 billion years, for more than 1 billion years. And so when that wave washed up against the Earth, it was only a tiny ripple. Now, the researchers at LIGO detected those tiny ripples in the space-time by carefully measuring the length of the long detector arms at the LIGO sites. So you can see that each arm, there's two of them at right angles, extends for 4 kilometers. And when the gravitational waves pass through that site, it stretches and squashes the arms by just a little bit. In fact, it stretches them by less than the width of a hair, less than the width of a virus, and in fact, less than the width of a single atom. And so this new observatory and the technology hidden in those buildings and those arms is really a remarkable feat of human ingenuity. It's quite exciting then that, in fact, India will have its own interferometer with LIGO India, and that is scheduled to be up and running by the end of the decade. Now, if we want to get a sharper picture or better resolution, there are really 2 ways that one can go. One is to improve the technology and to get better at detecting the change in the length of arms like this. And the other is to build much longer arms. And towards the second goal, in fact, there's going to be a new generation of gravitational detectors that are based in space. And indeed, instead of measuring the distance between endpoints on a 4-kilometer arm, they're going to be measuring the distance between satellites that are millions of kilometers apart. Now, work to develop this new project called LISA is well underway, and it's led by the European Space Agency in collaboration with NASA, and in fact, a whole international consortium of scientists. And it's expected to launch in about a decade from now. But one of the reasons that they and we are confident that this approach will work is that, in fact, there are already pairs of satellites that are measuring gravity in this way. And so, in fact, in this image, I'm not showing the LISA project. What I'm showing there are called the GRACE satellites. And GRACE stands for Gravity Recovery and Climate Experiment. This was an experiment, a joint work between NASA and the German Aerospace Agency, and it originally started, or it was launched in 2002. What's shown here is actually a follow-on, GRACE follow-on project, which launched in 2017. And so by carefully measuring the distance between those two satellites, one can detect subtle changes in the Earth's gravitational field. And of course, that gravity or that gravitational field is determined by its mass. So here in this image, what one sees is that the mass of the Earth is not distributed uniformly. The colors in the image represent what they call gravity anomalies, quite different than the anomalies the researchers and I work on, but instead what they're talking about here are deviations from a standard gravitational pull that would have been created by a perfectly smooth or idealized ellipsoidal model of the Earth. So red shows where the gravity is slightly stronger, and blue shows where the gravity is slightly weaker. And while we're seeing here that the mass is not distributed evenly, it's also true that the mass moves or changes over time. Now, what is it that moves in the Earth's mass? Well, it's really water. So with this image here, what they're looking at is the ice shelf on Greenland. And so what you see in the graph is actually the seasons playing out year upon year with increases in mass in the winter and then a dip in the summer season. But while it goes up and down, it's clear that there's a trend and that the glaciers in Greenland are slowly melting. Now, GRACE can also track what's happening in aquifers under the Earth. And so in the image on the right here, we can see what's happening in the groundwater here in India and across the rest of Southeast Asia. So now back to the question, what is theoretical physics good for? Well, here is half the answer. It's good for precisely what we see on the screen. Theoretical physics is a seed. It starts with an Einstein, and it takes us to black holes, from black holes to gravitational wave detectors. And with that, we get images of groundwater that we just couldn't have taken in any other way. So theoretical physics puts climate data in the hands of policymakers in Geneva. It puts a phone in the hands of a farmer in Nigeria, and it might put an MRI imaging machine into the hands of a doctor here in Bangalore. So investing in theoretical physics rarely pays off right away, but it almost always pays off in the long run, and the payoff is enormous. I said that was half an answer. What's the other half? Let's think for a moment. If the COVID pandemic taught us anything, it's that we do not know what problems the future will throw at us. We know there will be many. Climate crisis is real. The pandemic of a few years ago won't be the last one. There are global inequalities, environmental degradation, food security, the list goes on, and it's a very long one. Those problems are real. And we also know the resources for addressing these problems are finite. There's only so much time, so much talent, and so much energy in the world. These constraints are also real. So given our problems are urgent, given that our resources are finite, what are we doing? How do we justify spending our time, as many of the people here today may have been spending their time, studying holographic entanglement entropy or von Neumann algebras? How do we justify purely curiosity-driven explorations like that? The truth is, we don't know exactly how breakthroughs in fundamental research, be they in physics, in biology, or any of the other sciences, will change the world. But it's vitally important that we invest in and strive for those breakthroughs anyway. Let's look back at the COVID vaccine program. In the wake of the emergence of COVID-19, private companies and governments made big investments. Scientists around the world worked together, and effective vaccines were available in just 11 months. That's faster than any other new vaccine had ever been developed. It was a miracle that saved perhaps millions of lives. Now, many of the COVID vaccines were a new kind of vaccine called mRNA vaccines, or messenger RNA vaccines. So why did we end up with mRNA vaccines just when we needed them? And the answer there is because of decades of fundamental research. The discovery of the science of heredity goes back more than 100 years. The discovery of the molecules of heredity, DNA and then RNA, goes back some 50 years. And these discoveries weren't made with vaccines in mind. They weren't made with anything in mind other than that the scientists, or we as humans, wanted to understand the world in a more fundamental way. And of course, that work kept going. In the 1970s, we learned to sequence these molecules. In the 1980s, we learned to make mass copies of DNA. And in the 90s, we learned to use RNA to express proteins in vitro, that is, in glass test tubes in the lab. And then came further decades of uphill work that made it possible for the discoveries and the advances towards practical vaccines. Now, it must be said that at many turns, these advances came with the dogged determination of the scientists. Here, Kathleen Karioko, well, she's a Nobel Prize winner, but she's hardly a household name for most of us. Yet her persistence over decades in this field, in the face of skepticism, in the face of funding challenges, really laid the foundation for the rapid development of the COVID-19 vaccines. And when the COVID vaccines were released, some people were frightened. They wondered if everything had been rushed. But of course they hadn't. You know, the vaccine developers hadn't skipped a single safety step. Instead, they were able to quickly build on that solid foundation of work that had been built over decades of research. So my point is that the science hadn't been rushed. The science was much older than anyone talks about, and its roots went very deep. And at the very root is just the curiosity of the scientists. It's research like this that lets us move beyond the narrow horizon set by our problems into a larger world, a world whose horizon is set by our imagination. If we understood how curiosity-driven research into biology leads to vaccines that may save millions of lives, if we could map the path from A to B, then life would be easy. We just invest a lot of talent and money and energy into A and simply wait for the payoffs to roll out in B. But it doesn't work like this. We rarely see that path. A medical researcher named Samuel Broder used to direct the American National Cancer Institute in the United States from 1989 to 1995. And the researchers at that institute really did some amazing work over that period. And so it might be surprising that Dr. Broder was actually opposed to a centralized whole of government effort to fight cancer. In trying to explain why, what he said was that if it had been up to the government to cure polio, we'd have the best iron lungs in the world, but we'd have no polio vaccine. In other words, the government would have invested in the best and most promising technologies we had, the things where the path from A to B was obvious, but they would have tackled our immediate problems head on. But if we invest all our energy in those immediate solutions, we'll never get past the horizon of our problems. What I'm saying is not that we shouldn't tackle those problems. Of course, we should. We must. If people can't breathe, then we should develop iron lungs. But we should also take chances on those long shot ideas, the vaccine type ideas. And even beyond that, we should take chances on what we call those blue sky ideas with no practical aim at all, the Einstein ideas, if you like. Fundamental research, curiosity-driven research is so important, not because we know it will pay off, but because it lays the foundation for a different kind of a world. It is the deep work that we do today that makes the immediate solutions possible tomorrow. We dig deep so that we may build high at some point in the future. Now, I want to take this argument one step further. I've said that we should move past the horizon set by our problems and move towards the horizon set by our imaginations. But beyond our imaginations, there's another horizon, an even bigger world, the world of what's possible. Now, how do we reach towards that third and possibly largest horizon? How do we find a world that is literally beyond anything that we can imagine today? I would argue it's exactly by pursuing the kind of research that inspires people, purely driven by our curiosity, and not what's that good for. This, of course, is not a new idea. Almost 90 years ago, Abraham Flexner published a short essay titled On the Usefulness of Useless Knowledge. Now, Flexner was the founding director of the Institute for Advanced Study, a center for theoretical research in Princeton in the United States. It was the home of many of the 20th century's greatest minds, Albert Einstein, Robert Oppenheimer, John von Neumann, and many others. Flexner's essay was published in 1939 in the United States. It was a country that was caught in the teeth of the Great Depression, and it was caught in the grip of a climate crisis known as the Dust Bowl. And what Flexner did is he argued for pure curiosity. Now, the opening story stuck with me, and so I'd like to share it. Flexner recounts a conversation he had with George Eastman, one of the founders of the Eastman Kodak Company. He was an inventor and an entrepreneur, but beyond that, Eastman had founded the Bureau of Municipal Research to help make scientifically driven government policy. He could have almost been one of those reviewers that were participating in my thought experiment. The timing's only off by a few years. Now, Eastman told Flexner that he wanted to devote his vast fortune to the promotion of education in useful topics. Since they were talking about usefulness, Flexner asked Eastman who he regarded as the most useful worker in science. Eastman replied, Marconi, of course. Now, this was a reasonable choice from Eastman's point of view. In 1895, Guglielmo Marconi built equipment and transmitted electromagnetic signals from one end of his house to the other, and then from the house to the garden. If you read history books, you'll see that this was the dawn of wireless communication, the dawn of radio. Now, this was the information technology that stitched together the world as Eastman and Flexner knew it. And so Eastman chose Marconi as the most useful. But Flexner's response was Marconi was inevitable. The real credit should go to James Maxwell. This was the person who had figured out that electricity and magnetism are part of the same force and that they move together in waves. We now know as light, and radio. That work began in 1865, and Maxwell published his equations in 1873. Then came 15 years of fast-moving, pure science and the birth of a new field, a new technology, a new era. Maxwell had no practical objective in mind, and he saw no practical applications. In fact, another scientist, Hertz, actually said as much. You know, Hertz was the inventor of something known as the spark gap transmitter, which he built a decade before Marconi's invention. But when he was asked about it, Hertz said, "This is of no use whatsoever. It's simply an experiment that proves that the Maestro Maxwell was correct." And that was enough for him. So people like Hertz and Maxwell, people like me, like the researchers at Perimeter, or the scientists here at the ICTS, we're just explorers driven by our own curiosity, not by usefulness. And so Flexner's essay goes on to argue that most of the really great discoveries that have changed our world were made by men and women who were driven not by a desire to be useful, but merely by the desire to satisfy their curiosity. Now, a book with Flexner's essay sits on my shelf back at Perimeter because, as I was saying, I'm the director of an institute. And it's a place where people try and understand nature at a deeper level, and of course, with no real practical application in mind. Now, the Perimeter Institute, like the ICTS, is not a university, but a center of research. We have 200 researchers, from master's students to world-leading scientists. We're one of the largest independent theoretical physics institutes in the world. And Perimeter is also a fairly young institute, as the IAS was in Flexner's day. It's young enough that I can tell you the origin story because I was there. Perimeter's founding donor was Mike Lazaridis. And Mike is the gentleman who took pagers and hooked them up to the internet and created the BlackBerry. When I first met him, in fact, it goes back to the fall of 2000, and he was in the middle of transforming his BlackBerry and inventing what became the world's first full-fledged smartphone. And I think he knew that he was about to reshape the world. But that day, that morning, when I met him, he didn't want to talk about any of that. He told me what I had told you earlier, that the smartphone is a triumph of theoretical physics. 150 years of breakthroughs packaged in a sleek little box. Now, Mike is a physics enthusiast, and he was well aware that in a story that ends with a smartphone, he's another Marconi. He's aware that the Marconis are probably all inevitable. But what about the Maxwells? Those are the wild cards. That's where the magic is. Now, Mike wanted to know where the next Maxwell would be doing his work, or put in another way, if the smartphone relies on breakthroughs, then where would the next breakthroughs come from? The ones that would shape the lives of our grandchildren and our grandchildren's grandchildren. But he had an answer. He had a bold idea. His idea was to create a new physics institute. It would bring together some of the best minds in the world, tackling the deepest and most difficult problems in physics. And that was the first time that I heard about Perimeter. But I was struck by Mike's vision, by its simplicity, its clarity, and its audacity. It really stuck with me. And a few days later, I found myself calling Mike to say, "I'm in. How can I help?" Soon after, I left a tenured position at a distinguished university with traditions reaching back over 100 years. And I left it for a place that didn't really exist. At the time, Perimeter was barely more than an idea. When I arrived in Waterloo, there wasn't even an office for me to work in. People told me that I was crazy, and maybe they were right, but it was the right move. Now it's almost 25 years later, and Perimeter is really a world-leading institute. We look at things like quarks and qubits, we work on black holes and big bangs. We're really working to understand the universe at a basic level. And so almost every day as director, people ask me, what is this all good for? And of course, as I've been explaining, the honest answer is we don't know, just as Maxwell didn't know, Einstein didn't know, just as the pioneers of quantum theory didn't know, just as the biologists who discovered DNA and RNA didn't know. And I have to admit that some of it will not be good for anything at all. We need to acknowledge that. Moving beyond the horizon of our imagination is not an efficient process. Nevertheless, if we try to predict what will pay off, if we make promises of returns on investment or advancing key performance indicators, we're putting science in a straitjacket. And most often, we're simply wrong. So I want to give you an example at Perimeter to illustrate this. And so I want to go back to one of my early slides here. And what you see around the globe are 9 different areas of physics, including cosmology, particle physics, and quantum information. But in that list, there's one dark horse in the lineup. The last place you would have placed your bet for a payoff, or even a long-term payoff. And that's the one down here at the bottom, quantum foundations. Now, quantum foundations concerns the underpinnings of quantum theory. You know, what does the theory really mean, conceptually and mathematically? In the early 2000s, it was really a backwater of theoretical physics. Most physicists thought of it more as philosophy than science. And in the early days, when I would go around and try and explain Perimeter, describe what it is and what it would become, when I came to quantum foundations, most people voiced skepticism, and some people actually laughed in my face. But Mike Lazaridis, that smartphone fellow, really insisted that quantum foundations should be a part of this new institute. In fact, it was one of the very few things that he insisted upon. And so we hired some quantum foundations experts, very much against the prevailing view. And if we fast forward now by some 24 years, suddenly one of the most exciting new things, one of the new directions happening at Perimeter is being driven by our quantum foundations team. And it's known as quantum causal inference. Now, I should explain causal inference without the quantum. And this is the detective work that allows researchers to draw cause and effect relationships from data. It's a domain of statisticians and computer scientists. Many of us have probably heard the maxim that correlation doesn't imply causation. But causal inference researchers are developing statistical tests that they can apply to the data that do let them say things about cause and effect. It's a field that takes on questions across a vast number of areas. In fact, any area where people are collecting large amounts of data. For instance, one might consider a medical trial where a group of patients receives a certain drug and 63% are getting better. Now, does that mean that the treatment is effective, or does it mean only healthy people signed up to enroll in the study? A central bank might raise the interest rates and the stock market rises. Now, was the market reacting to the monetary policy, or was it some other factor? Does our practice of putting out wildfires in the Canadian North lead to wildfires getting bigger over time? Or is it being driven by climate change, or perhaps both? Perhaps, again, there are other factors in play, factors that we can't see or can't even imagine. The unknown unknowns, as it were. These are the kinds of questions that causal inference researchers might delve into. So that's causal inference. Where does quantum foundations come in? Well, perhaps the most famous result in quantum foundations is known as Bell's theorem. Now, John Bell was a researcher who worked at CERN in Geneva, and in 1964, he proposed a test of the very nature of our reality. Now, the details are complicated and they're subtle, but let me try and explain it this way. In the early days of quantum, and in fact in Bell's time, many researchers thought that quantum theory might be some statistical approximation of some simpler underlying theory. Much as we speak about the temperature or the pressure of the air in the room here. We assert that these are properties of the air, but we actually know that they represent some approximate or average measures of the behavior of the atoms and the molecules that make up the air. And hence many people in turn hope that there was another layer of simpler physics, or at least conceptually simpler, that underlay the quantum theory. Now, Bell's thought experiment that was later carried out and confirmed in the lab involved two researchers making a set of independent measurements and then seeing how often their measurements agreed. Bell developed a statistical test that let him say that if the measurements agreed above some threshold, then there could be no underlying simpler set of physics. So it was something outside, or it was something really quantum was happening that at the heart of it. Now, for decades, quantum foundations researchers had used Bell's work like a microscope to get a deeper look into the nature of quantum theory, and they also found other powerful tools, new statistical tests, that they could put alongside Bell's theorem, and nearly all of those tests boiled down to very similar statistics. Now, in 2012, one of the quantum foundations researchers at Perimeter, named Rob Speckens here on the left, had the insight that the statistical test that is Bell's theorem could be recast in the language of causal inference, that is, in terms of cause and effect. And in fact, that's when the penny dropped for Rob, and he realized that quantum physicists were actually sitting on decades of results about causal inference, even though no one had thought about it that way before. Now, causal inference is a remarkable new way to think about quantum theory, but at the same time, Rob realized that the ideas and the techniques of quantum foundations, like Bell's theorem, could help advance causal inference, and in particular, to help identify those other factors or those unknown unknowns. Now, Rob was joined by another young scientist, Ellie Wolf, on the right, and they formed a small team to develop these ideas, and now they collaborate with medical researchers, with insurance companies, and artificial intelligence folks in a brand new field that we call quantum causal inference. So if Bell's theorem is like a microscope that lets us see subtle differences between the quantum world and the classical world, then what the quantum causal inference researchers are doing is finding ways to take that microscope and apply it to other problems in economics, in medicine, in climate science. It's not that we think that there's something quantum underlying a problem in economics or in medicine. Rather, it's that the microscope is so powerful that it gives us a sharper resolution on those problems and any problem where there's a lot of data. Now, it's a data-driven world in this modern age, And so this is really a remarkable result, and one that has a real power to make immediate and useful impacts. However, 24 years ago, if we had bet on what at Perimeter was going to have a useful payoff, especially within the tiny window of 20 years, no one would have chosen quantum foundations, and we would have all been wrong. But we didn't bet, we were curious, and we explored. And that's why the question, what's that good for, is so hard to answer. Now, I started the talk with a thought experiment about Einstein, just starting his career. Let's rewind to that time, 100 or more years ago. Let's think about the world of Einstein, the world of Emmy Noether and her marvelous theorems, the world of Schrodinger and his imaginary cat, the world of Niels Bohr and his model of the atom. They all worked in physics at about the same time. And if they wanted to visit each other, what did they do? Well, they went by a horse-drawn carriage, or perhaps a train drawn by a steam engine. If they wanted to communicate, they would write letters, or in a case of urgency, perhaps send a telegram. If they wanted to work in the evening, they'd work by candlelight, or perhaps by a gas lamp. And remember that at the time, this was really seen as the most advanced period of human civilization. And if you ask them what they were interested in, what are you working on? They might have talked about thought experiments with clocks and trains and light. They might have talked about the way that a grain of pollen moves about when it lands on the surface of a water. They might have talked about the colors that a poker emits when it's heated in a fire. Now, these weren't the pressing problems of the day, as I described before, but these brilliant people were curious. They wanted to know how things worked. And if you ask them about the future, they might have talked about the possibility to build steam engine-driven carriages or made other laughable predictions. They simply couldn't have conceived of or imagined the world that we live in today. That's a world of space satellites, of commercial air travel. It's a world of supercomputers, of smartphones. All of these ideas, those concepts, all of that technology were simply inconceivable in the early 1900s. And yet the esoteric research which they did in those days, even useless research, that work laid a foundation. It laid the foundation for many of the things that we take for granted today. So what's fundamental research good for? It's precisely for that. It's good for laying a foundation for a future world, a world we cannot imagine. In fact, if I were trying to guess on the impact of today's fundamental research and how that would change our future world, I know I would be wrong. I know that my predictions would be seen as unimaginative, as laughable, and make me appear as even dull-headed. And so I'm not going to do that. Instead, what I'm going to do is I'll say this. Our world was once defined by scarcity, by fixed resources that never seemed enough to go around. Our problems today can seem insurmountable. We can feel like the delegates at that very first urban planning conference. What they didn't realize, and what we sometimes forget, is that solutions are possible. Solutions that we cannot even imagine. So curiosity-based research has laid a foundation for a new kind of a world that expands and creates more for everyone, creates health, it creates wealth, it moves us across oceans and into space, it spreads our ideas through the air, and it puts all of human knowledge in our pockets. It feeds us, it creates wonder. What will be the phenomena that change our world? or change the world of my grandchildren, my grandchildren's grandchildren? I can't say. And I'll simply say, though, that I'm an optimist. And I hope that this afternoon I've shared some of that optimism with you. The world's problems are very real, they're pressing, but they should not define our vision. We have to think about a horizon that goes beyond our problems and even beyond the horizon of our imagination. We have to try and strive towards the horizon of what's possible, because that's unimaginably rich and beautiful and large. And it's with our eyes on that horizon that we all should explore. And so with that, I'll end my talk and I'll thank you for your attention.
Thanks very much, Rob, for that very eloquent kind of pain to curiosity and the science that we all do. So before we take on questions, I want to just present to Rob a small memento from ICTS.
Thank you.
It's a jacket and a mug,
Okay.
just a keepsake from your visit.
Okay.
So Rob will be happy to take questions, and you can put up your hand. Someone will come to you with a mic. So over there, I see a hand up. Please keep your questions short and more or less to the topic of the lecture.
Good evening, sir. It was an amazing session. I really enjoyed it, and I could really find value in what I'm doing, what I was doing today. And one question I was very intrigued by is that what is the relevance between energy and information? Just centuries, 1 century ago, Einstein created a relevance between energy and mass. So, is there something that has a relevance which is close to E equals mc square in terms of energy and information?
Well, I'll give you two answers. One is that, you know, there are physicists for a long time, starting with John Wheeler, who thought that information or information-like questions underlay all of physics. And in fact, the kind of work that my colleagues and I are doing are really developing those kinds of ideas. Now, if you want a relation between energy and information, perhaps the closest would be that there are new relations discovered, perhaps in the last 5-10 years, which relate changes in entropy. And entropy is a diagnostic that can tell us how much information is captured in a certain region, and how those changes are actually related to the energy in that particular region. So there are some simple or relatively simple ideas that people are further developing as we speak. They're probably working away in their notepads in the back of the lecture hall here. But no, that's a great question, and it's one that people are studying as we speak.
Thank you, sir.
Yeah.
So, like, my question is, so in the past, people like thought that steam powered trains were like a miracle if it really happened in the future for them. And if we look now, they're like already electric trains and super fast trains. So my question is, the ideas that we talk about now were like our answer, like our I'm not gonna go. So our grandchildren and their grandchildren will like probably say it's not a miracle. It's like a part of our day-to-day lives. So how far do you think we are from that?
Well, that I think you're trying to goading me into answering the question that I refuse to answer, which is what is the work that we're working, or what research that we're doing now is going to have an enormous impact, 100 years from now. And like I was describing, people even like Einstein and Maxwell, they simply couldn't imagine where technology would go in the future. And yet, the work that they were doing, simply trying to understand how the universe worked, that really laid a foundation. New inventions, they don't pop out of the vacuum. They don't come from nothing. They're really building on the work of hundreds of other people who have sort of lead humanity to that particular direction and that particular invention.
So your imagination and someone.
Yeah, we're going to rely on
I
you.
think that's what's going to take us to the future. Yes, a question there.
Yes. Hi. Thank you. Yeah. Thank you
Hi.
for saying everything that you said. I think I also felt super validated as someone who's studying physics. But my question is, would making the study of physics more accessible possibly help answer the question, what good is this for?
I think you've hit on a very important question, and it's one that we recognize at Perimeter. And as Rajesh was saying, that it's part of the pillar here at the ICTS. But it's really by making the science more accessible that we can, in part, I'm driven by, satisfying donors and politicians and getting funding. But really more important than that is that we're inspiring, or we hope to inspire, younger generations and make them realize that, they can make contributions. And so I'm looking at you, to our future research and our advances. Because as I was saying, I think that's really an important direction. And it's not to say it's the only direction. Again, I want to emphasize, there is room for the engineers and the technicians. And we have real problems that we have to work on today. But, that's not the only thing that we should be doing. And by, capitalizing on more human capital, or by bringing more individuals into that endeavor, we'll be able to both take on, those urgent problems, but also to accelerate the advances in the research, the fundamental research. I hope that answers the question.
Yeah. Thank you.
So I have a small question.
Okay.
So you're telling about Einstein, horse manure, and a simple thought experiment. So this reminds us, like, even today there are various thoughts, various things that we find bizarre. So even like in history, there are various things that sounded bizarre to the people of those times, but could be very helpful in the evolution of physics and evolution of sciences in general. So because of lack of support during that time, it couldn't be in the level it is supposed to be. So in relative to that, do you think the the support to physics, or the support to theoretical approaches, has it been changed, or it is the same now?
Well, I have to say, in Canada, that the Canadian taxpayer, the government, has been extremely generous. And, Perimeter could not exist without the funding that we receive both from the federal and the provincial government. I'm not sure what it's like here in India or in many. I see a
This is
nodding
a
head.
publicly funded institution paid by the taxpayers of India. And I think that's a testimony to the farsightedness of the founders of modern India, that they invested in institutions like us, TIFR, IASC, so on.
So my personal experience is that there is, or that the funding has been very generous. You know, we have to justify our work, and so that's why I give talks like this or have discussions like this. But yeah, no, there's been remarkable funding in many different areas.
Good morning,
Question
good evening,
there.
sir. I had a question. Once the funding for research has been given and some progress has happened over time, how do you prevent over corporatization slash industrialization of it? For example, like if we take quantum computing and the IBM, initially it was kind of focused on like pure research on how it can be applied, but nowadays they are trying to focus more on like NISQ, like noisy intermediate scale, uh, short-term applications. So how? But I imagine that in the long run, most of the big applications will happen from a pure research or theoretical perspective. It will come from that background. So once funding has happened, how do we or should we prevent the over corporatization or like industrial focus?
I'm not sure that I really want to prevent. Perhaps it's the word total, and I don't think that's the case. I mean, I can point at other examples at Perimeter. For example, there's an initiative called the Perimeter Institute Quantum Intelligence Lab, and what has happened there is we've sort of got a space where we've gathered together researchers, students who are working on AI or machine learning, and they're motivated by questions like, you know, identifying new phases of matter, or you know, very fundamental questions. But they sit side by side, in fact, with I call them still researchers who are connected with startup companies like, well, the founding company was something known as 1QBit, but there are other companies like Xanadu, IonQ, have researchers all working in that same space. And what I like to say is that, you know, they're motivated by different things, of course. If they're working for a company, they have applications, or they're trying to find applications in mind and develop those. But they're still sitting, I like to say they're playing in the same sandbox. I don't know if that goes over in India, but they're using the same tools and techniques, and they sit together, they share ideas, they talk about their problems, and both sides are actually, finding benefit in that relationship. I'd also say, well, that's one example at Perimeter, but you mentioned also NISC, these noisy intermediate scale quantum devices. These are really amazing platforms, and one of the things that they're not good for are doing, real quantum computing yet. However, they're marvelous platforms for discovery, for doing research. And so there are many examples where researchers, again, motivated by fundamental questions, are testing their ideas on these devices. And so again, there's a synergy between the researchers and in this case, the experimentalists, in that they're really, validating and testing the performance, really pushing the frontier of what they can do with these devices through addressing fundamental research questions.
Yes, so and like just a small follow-up. Then like, how do you think we can help bridge this gap between industry-oriented people or create an environment in which
easy flow of collaboration can happen, because these things are seen quite often in the West and places like maybe perimeter, like you've mentioned. But in India, there's quite a sharp distinction between what is academic research or theoretical research and that which is industry oriented research. So, what steps do you think can be done to help them collaborate in a more efficient manner?
Um, that's a great question, and I'd have to understand more about the culture, about the framework, the situation here. But in perimeter, again, it was just one of those things that we experimented with. The quantum intelligence lab, we didn't know how it would work, or but we just or well, I had faith in the person who led that project, and he thought this was a good idea, and we just tried it out. And in fact, it really blossomed and has grown. So just by trying new things, trying for new collaborations, I think giving them a chance. Not everything is going to work, but just giving them a chance is a good place to start.
Yeah, no, uh, I think that space and creating the sort of the space for people to talk, interact, I think is very important. Even at ICTS, we are trying to start something, a lab, but in a probability statistics lab, which would bring together mathematicians, computer scientists, and even some physicists to maybe talk with people in government, in industry, in many other areas where, of course, and this actually started from some engagement during the COVID pandemic when data for the spread of the pandemic had to be collected, analyzed, and sort of the countrywide and in Karnataka state especially. So there are possibilities like that, and I think you have to create these spaces. And perimeter, that's a great example, which in the quantum intelligence lab. I hope many institutions in India will create these spaces in the future.
Thank you, sir.
Any? Yeah. Just a second, just hold on. Someone will get a mic to you. After that, okay.
Hello, sir.
Hello.
So my question is, in physics also we have different areas catering to different sectors of our progress. In theoretical physics, we have many things, many different aspects in which physics influences. So I want to know how society also influences physics in a certain way. How should we progress and do things like the way different areas of physics cater to the different needs of society in different ways. How do we balance with different things like that? I mean, different aspects of society scatter to the that.
Well, I think, we have to, well, the first thing I'd say is that research, fundamental research in any field is a human endeavor. And we're all a part of society. I think, what Rajesh was mentioning in responding, say, to an urgent crisis like the COVID pandemic, I know we open dialogues with various people as well. But I think on the whole, it's perhaps by creating spaces like Rajesh was talking about, where different communities can talk together and share ideas. And certainly, that is part of my job, that I have to talk to all sorts of different sectors, all sorts of different kind of communities. And it's something that we're developing programs so that it's not just the director, but that we want to give the researchers themselves the tools to communicate effectively with, people who are, perhaps enthusiasts about physics or curious about physics, but don't have the same background or expertise that we do.
Okay, we'll take one last question.
Excuse me,
Okay,
sir.
we'll just have
Sir.
this question and then the last one there. Yes.
Oh, there's another one here, but.
Hello.
It'll probably
Okay.
have to probably cut off at 5:30, but
Okay.
yeah.
Thank you for the talk, sir. Sir, as a graduate student stepping into PhD, I wanted to ask that, let's say I want to get admission into, let's say, perimeter or somewhere anywhere. I need to, have some published works, right? So because we live in a society where we are constantly measured and we compete, right? And then you are talking about choosing the path of led by pure curiosity and everything like that. And you yourself agreed that there is no guarantee that you can reach from point A to point B. It's like a random walk. So let's say if I pick up questions like from string theory and cosmology, where there is too much investment, too much hard work, and there is no guarantee that I'll get published works so that I would be selected for a good postdoc, say. So how does one balance these two things, that picking up the right questions which can get you published works and also led by curiosity? Or is it just during this time, or I think even professors face the same problem perhaps, because I heard about this publish or perish culture, right?
Yeah. The number one thing I would say, if you're a person just setting out on a PhD, is to identify a topic that you yourself are enthusiastic about, because you're going to be spending many years, many hours, long nights, working on problems in that particular area. And your enthusiasm or your energy it'll have to be there for you to carry through all of that. As you said, there are no guarantees and there's no magic formula, but something that I tell even the junior faculty is, there are the really big questions, the ones that we think are, the most exciting, but they're also the most challenging. And so you should balance your studies or your research to have a portfolio, not just of those super hard or super exciting questions, but also ones that, may seem like smaller advances, but still are making contributions to advance the science.
Thank you.
Okay.
Sir,
The-
sir,
the
here.
last question up there. Yeah.
Good evening, sir. My name is D. Hiren Kumar from St. Joseph's University. And I have a question that should there be limits to what we seek to explore or discover? And if there is, what is the need for such limits?
Well, there are, I guess it comes back to questions about society. And I'm not thinking now about physical or physics, theoretical physics, but I'm thinking about biology and the research that we might be doing there. And so that's a place where, as a society, we have ethical standards, and we may choose to allow some kinds of research and not others. And I think that's, as I said, research is a human endeavor and we're all part of a society. And so that may be imposed in certain areas. I'm not sure if that's the question, but.
I have a follow-up now. What if
okay.
society doesn't play a role?
Society doesn't play a role?
What if society is out of the equation itself?
Well, I think ultimately, again, something that's important or that we've mentioned earlier is that funding is important. And I think society is not out of the equation at any stage.
No, it's just an assumption. Like, what do you say, a hypothesis?
It is a hypothesis, but it's one that's been supported by perhaps my lifetime or my career in science. So all I can do is share with you, what my experience is.
Okay, sir. Thank you.
Okay.
Okay, thank you everyone, and great to have all of you participate in this wonderful lecture. And please tune into other ICTS events as well. We have Copy with Curiosity. I don't know, maybe many of you have heard of it. It's in the planetarium, so you don't even have to come all this way. I think there is one coming up next weekend, I think. Yeah, this coming weekend, it's on mathematics, on the so-called ABC conjecture, a very fascinating mathematical story and a sociological story by Min Young Kim. I think you'll enjoy the talk. There's several others, and you can always check out our ICTS talks on YouTube, our YouTube channel, for lots of the past talks and many others. So thanks again for coming, and there's high tea outside, and thank you all. And thanks again to Rob.